the state of stress at a point in equilibrium will allow us to conduct our engineering analysis. So far, we have shown that the state of stress when the system is getting buried is basically controlled by the vertical effective stress, and in that case, under zero lateral strain, we were talking about the K0 state of stress. However, the situation may get more complex. For example, if an earthquake comes and imposes shear stress, or if there is a shear force applied on the surface, for example, when a truck brakes on a pavement close to a traffic light, or if there is an excavation that takes place that tends to drive the system in the horizontal direction, causing shear on the element. The question is, how can we understand this state of stress in the context of continuum mechanics? And now you can do that with algebraic formulations, with matrix formulation, very effectively. But I would like to keep the concept of Mohr circle alive because it's such a simple, versatile, and so clarifying from the point of view of deriving all the equations that we will need for soil mechanics and engineering analysis and design. So the question is, what is the state of stress if we cut that element and we impose along that direction theta, we impose the stresses that will be needed to maintain that element in equilibrium. So I will have to impose stress normal to the plane theta and a shear stress parallel to the plane theta that will maintain the system in equilibrium. Let's plot these two parameters versus the direction, versus the angle theta. So when the plane is horizontal, then I only have the vertical stress. So if we make a polar plot of these two quantities, when, once again, the theta is equal to 0, I only experience sigma vertical. However, when theta is horizontal, I only experience sigma horizontal, whether I look to the left or to the right. So this is the polar histogram of normal stress. In other words, in any direction, direction theta, this quantity here is sigma theta. However, if I plot tau, we can do a similar analysis. When the plane is cut at the horizontal direction, there is no shear. When the plane is cut in the vertical direction, there is no shear either. But as you can readily see, when they're at intermediate angles, there will be significant shear required to maintain equilibrium. So actually, this diagram will look as follows. And you can see the equations. These are basically sine and cosine functions when you solve this system of equilibrium equations in the vertical and the horizontal direction. When we add shear, the story gets a little bit more interesting because we have not only the normal stresses, but we will have to put the shear. And if we place the shear, like for example, a track imposed on the surface, now that creates a moment, and that moment is going to make this element spin and accelerate. Therefore, in order to satisfy equilibrium conditions, the summation of moments with respect to the center must be equal to 0. Consequently, as soon as I apply shear, there has to be reciprocal shear stresses imposed on the element that will prevent it from spinning. So we have both force equilibrium and moment equilibrium for that point not to accelerate either axially or spinning. Now, what is most surprising is that in this case, I plotted the normal stress and the shear stress with respect to the direction theta. But now, let's think of a weird thought. What happens if we plot each of these values of normal stress versus shear stress, the shear value in the direction theta and the tau value in the direction theta, and if I do that for one angle of the plane theta, I will get this point. We said for 0 angle, I will get the vertical, and then I keep going around, and all of a sudden, I define a circle. And this is really quite surprising. Of course, it's all written in the mathematics, but it is quite surprising, and it's a wonderful observation from Mohr in the 19th century. So what is Mohr circle? Mohr circle is a graphical representation of the state of stress at a point in equilibrium when you use the tau sigma space with equal scaling of tau and sigma. Mohr circle is a state of stress at a point in equilibrium. So let's see how to draw the circle. Let's consider the following state of stress, which is going to be defined by the vertical stress, which we're going to say is 10, the horizontal stress 2, and shear stresses with proper reciprocity, let's say 4. Now, the first thing that we need to do to draw the Mohr circle is to establish a sign convention. So let's say that this is going to be positive when the stresses are normal to the body and when shear causes counterclockwise rotation. With that convention now, we can draw in a tau sigma space, which is equally spaced in y and x. We can draw the horizontal and shear stresses. This is going to be tau. This is going to be sigma. And let's split the space in pretty much equal quantities. This is 5. This is 10. And here we have another 5. So the first thing next is to plot a point in the tau sigma space that represents each of the faces. Basically, we need to plot two faces. So let's assume that the face here at the top is going to be face A, and the face here on the side is face B. So plot the point that represents face A and face B, each of the points. So the point for face A is 10 normal, and the 4 creates a clockwise rotation. Therefore, this 4 is a negative value, so this is the point that represents the state of stress on face A. What about the point that represents the state of stress on face B? Is at a normal stress of 2, and the shear produces counterclockwise rotation, so it's positive 4. So this is the point that represents the state of stress on face B. Where these 2 points intersect, they define the center of the circle, which is going to be at 6. Please note that point A and point B are on opposite sides in the tau axis. Indeed, this is because of reciprocity of shear stresses. And because of reciprocity of shear stresses at a point in equilibrium, the circle is always centered at tau equals 0 on the sigma axis. So now we can try to draw the Mohr circle center at 6 and going through point A and point B, and with some error with this graphical representation, that is our Mohr circle. Now we can do many important observations. So once we draw A and B, now we can draw the Mohr circle center once again at the intersect between A and B. At this point, we can identify many important elements in the circle. One of them is that this is the maximum stress. We're going to call that sigma 1. And this is the minimum stress. We're going to call this one sigma 3, principal stresses. On those 2 points, there is no shear component, and therefore these are principal stresses. Now we can also say what is tau maximum, which is that point, and as well as this one. And we are ready now to use the circle. This was all for drawing. The next one is to use it, and to use it we have one important element. We need to identify the origin of planes. The origin of planes is identified as follows. Draw through point A a line parallel to face A. So we draw through point A a line parallel to face A. Face A is horizontal, so we draw a horizontal line, and it's going to intercept somewhere here. This line is parallel to face A. It may sound arbitrary, but please recognize that if we draw through point B a line parallel to face B, so we draw through point B a line parallel to face B, we intersect at the same point. We call that point the origin of planes. And you may say, and why is that point so important? Well, this point is unique. And I will demonstrate next, but let me first of all tell you how you use the Mohr circle now to identify any stress in any direction. So now let's use it. And in order to use it, you're going to draw through the origin of planes, through this point, a line parallel to any direction of your interest, any direction theta. Let's assume that my direction theta looks as follows. This is theta. So I would like to know what is the normal stress and the shear stress I need to apply on that plane theta in order to preserve equilibrium if I cut off the rest of the element in this free body diagram. So I draw this line through the origin of planes, and this is a line at the theta angle. And now where the line intersects the circle, this amount is the value of tau theta, and the distance to the origin will be the value of sigma theta. So this value here to the origin is sigma theta. So I was able to identify the state of stress at the direction theta. I can do that for any direction theta. Now I can use the converse relationship. By the way, notice that there is a little bit of Maxwell reciprocity in this procedure. The same methodology I used to define the origin of planes from a known state of stress and directions, now I can determine the state of stress in any direction from the origin of planes. Let's see one more implication. What is the direction for the principal stresses? And so what are the principal stress directions? Well, let's follow the same logic. This is sigma 1, and this is sigma 3. So if I join the origin of planes with sigma 1, that gives me the direction on which sigma 1 is acting. In other words, I can take that line and plot it here, and I know that sigma 1 will be acting in this direction. And I can also do the same for sigma 3, and this is the direction for sigma 3. And because of the properties of circles, these two lines are always normal. This is sigma 3. So now I can redraw the element, rotate it into the principal stress directions. And by the way, here is the actual definition of the origin of planes. The origin of planes is unique because If you know the principal stresses and the principal stress directions, those two come together to define a unique point on Mohr's circle, and that is the origin of planes. So this is how to define the origin of planes, and this is how to use Mohr's circle. Let me summarize. From a known state of stress, identify the positions of the points on the tau sigma space that represent the known state of stress on two normal faces. By reciprocity of shear stresses, you combine those points. It defines a point at the center on the tau equals 0 axis, that means along the sigma axis, where the circle will be centered. You draw the Mohr circle from that center across points A and B, and that is the state of stress at that point in equilibrium. The next step is to identify the origin of planes, which is from either A or B. You draw a line parallel to the face that A or B are acting on. They intersect the circle at the origin of planes. From the origin of planes, you can determine the state of stress in any direction, or if you know the state of stress, you can determine the direction. And the origin of planes is unique because it's where the principal stress directions intersect, starting from the values of the principal stresses. One final observation. If you have a Mohr circle, the position of the apex is totally descriptive of where the circle is. I mean, in order to define a circle, you need 3 parameters. In this case, one of them is known. It's going to be at the center beneath the apex, and it's going to be centered on the tau equals 0 axis. So that's one unknown. The other two is the xy position, the tau sigma values at that point. Therefore, I don't need to draw the Mohr circle every time because it can get very messy. And I only need to plot the apex because knowing the apex, you can always go back, drop the line, and draw the Mohr circle. The apex is critical, and let's call the position of the apex, the distance to the origin, P, and in the vertical direction, Q. So P, the central position of the circle, which is the x-axis of the apex, is going to be equal to sigma 1 plus sigma 3 over 2. And Q is this height, which is half the diameter. In other words, sigma 1 plus sigma minus sigma 3 over 2. There are other definitions for P and Q values, and they come from the octahedral state of stress, and they take into consideration also the mean stress, sigma 2. They are intimately related depending on the state of stress, but we're going to continue with this simpler formulation, which is based on the Mohr circle. Please remember, if you have the coordinates P and Q, you have a fully defined state of stress at the point in equilibrium.